3D printing of Geneva mechanism. This video presentation will cover introduction to mechanism. So next will be modeling of the parts and assembly, and then last part will be 3D printing of those parts and assembly. This course is introduced for first year engineering students. The main objective is to give an introduction to basic mechanisms of mechanical engineering, and also students should able to create those models using CAD software package and use 3D printer for printing. The syllabus goes like this. So here this presentation will cover the 3D printing of Geneva mechanism, also called as Maltese cross, is a gear mechanism that translates a continuous rotary movement into intermittent rotary motion. So you can make out from this animation clip. Here this one disc is making a continuous rotation and other disc is making intermittent movement. That means the rotating drive wheel is usually equipped with a pin, that is, this is the pin that reaches into a slot located on in the other wheel. This is the driven wheel and advances it by one step at a time. The main wheel also has an elevated circular blocking disc that locks the rotating driven wheel in position between steps. So application of this mechanism will be in film movie projectors, counting machines, indexable equipments and clocks, etc. So there are three parts. So one is this continuous rotating disc, another disc which makes intermittent motion, which has slots like this, and a base which supports all these elements. The sequence of operation of this mechanism is shown here. The details of the parts are shown in this slide. So totally there are three parts. So part 1, which makes intermittent motion, part 2, which makes continuous rotation with a pin, and then a base which supports these parts. And the assembly of these parts is shown in this figure. So now 3D modeling of parts. So software used is Autodesk Inventor. So part drawings are here. So 3 components. This is part 1. So part 2 and part 3. Assembly drawing is like this. So now I will show how to create 3D models of these components. So first I will start with this. So in new I'll select metric units, standard mmi.ipt. So this part contains 4 slots. So that means for one complete rotation of the disk, driver disk, this makes rotation of 90 degrees. So now modeling of this component. So select sketch. I'll select this plane. So I will just create this drawing exactly as it is. Inner circle is diameter is 6 mm. I'll take little bit wider, so it is it's okay, 6.0 is okay. And then one more disc, sorry, one more circle of diameter 29, that is this one. Okay, so this circle is diameter 29, so 29. And then the last circle, bigger one, it is diameter 72. Now I'll take the reference line from here to here, and it is the width of the slot is so radius is 4.25, so it is 8.5 is the width. We'll offset this, so selecting offset option, offset. So from here I will draw a tangent uh, circle. It's a tangent to these lines. Now I will trim this. Okay, so now I will draw this arc, which is the radius is given, it is 28 mm. Radius is 28 mm. Now to draw this arc, so the center of this arc is at a distance of 50.91, and from there it is a arc of radius 28 mm, and it is at 45 degree. So I will take the line command, angle is 45 degree, it is 50.91 mm is the radius. So this is the center. Now from here I will draw a circle of radius equal to 28. So it is taking diameter, so radius will become 56. So I will trim this portion which is not required here. Okay, so it is like this. Now same thing should come on all four sides. So I can use this option, circular pattern. Select this, and then the center is this. Total numbers required is 4. Similarly, again circular pattern. I'll select this arc, center, and then numbers required is 4. Okay, so I will use trim option. I will remove these portions. Right, so this is the, so this also need to be removed. Okay, right. So now it is completed. Extrude option, select the area. Distance is 10, projection. Thickness of the disk is 10 mm, so it is 10. So the geometry is created. So now you can see this is the part that is required here. It has 4 slots. So this is part 1. I will give the name for this. So now part 2. So metric standard mm. So sketch. First I will draw the bigger circle. Diameter is 87. Finish sketch. Extrude. It is 10 mm. Sketch on this plane. It is circle. Radius is 27.8. So 27.8 into 2. Okay, 55.6. I will draw a line from the center. It is 54 mm. Then from here I will draw a circle of radius is 45.5. It is 45.5 into 2. So 91 mm. I will trim this portion. This is not required. Sorry. This line is not required. I will remove this line. Extrude. This is for 10 mm. Okay, right. So now I will create hole in this. The diameter of the hole is 6 mm. Extrude. Here I am removing the material, so it should be this option, cut. So then this projection is required. It is 8 mm. So sketch on this plane. That projection is at a distance of 36 mm. Diameter is 8 mm. So extrude. So length of extrusion will take 10 mm is okay, I think. 10 mm. It's not given in the figure. Can be 10 mm. So this is second part. Part 2. So one more part, that is base. So part number 3. First I will create a rectangle. So it is 40, width is 40 and 100 mm into 40 mm like this. So center distance I need to maintain, it is 50.91. So from one end I will take 20 mm exactly at the center. This I can do later. So I will extrude this. Extrude. This can be 5 mm. Sketch on this plane. From center I'll take 20 mm. And one more for one more projection. This distance should be 50.91. So I'll create a circle. It is diameter 5 mm. And here, so two circles. That another circle I will create later. Finish sketch. Extrude this circle. To a height of 20 mm. I can use that sketch and make it visibility. Use a visibility option, that sketch will be displayed. You can use the same sketch. So this to a height of 10 mm. Okay, so on this plane I need to create one more sketch. So diameter is 5 mm. Finish sketch. Extrude. This is 10 mm. Is okay. Okay. I will hide the sketch. This is the base. I can avoid this edges. It's not given in the sketch, so I will make it these four corners. I'll keep fillet so it looks nice. Okay. Right. So this is the third part, base. So I can assign the colors also. I'm just giving color. I'm not assigning any material. You can assign material also, but since here it is not essential, I'm just okay. So just assign some colors so it will look nice. So now entering the assembly environment. So assembly environment, I will place base first, place grounded at origin. So I will place part 2 here. So part 2 should rotate about Z. Okay. Constraint. This axis should align with this axis. Apply. Okay, again this plane should be over here. So this is assembly. Now I will insert part number 2, sorry, part number 1. So before placing, I will rotate the model. It should be rotated about Z axis. Okay. Constraint. The axis should coincide with this axis. This plane coincide with this plane. Okay. So this is the assembly. So Geneva wheel. I will save this assembly file. Save as. Okay. Not save. So file save. Okay. So this is assembly. So now we need uh, part files to print them in 3D printer. Okay, so for each part we need to create a file. So we'll go one by one. So this is part 1. Okay, file. So file, export, CAD format. So select STL file, save. Similarly, part 2, file, export, CAD format, STL, select .stl format. Similarly, part number 3, file, save, export, CAD format, here save. So for 3D printing, this assembly file is not required. It's only the part files. So we need to convert into STL files. So there are 3 STL files. Okay, so uh, yeah, so this is what is required. Okay, so these part files in STL format will be sent to will be given as a input data for 3D printer.
This session is on 3D printing. The 3D printing process builds a three-dimensional object design CAD model, usually by successfully adding material layer by layer, which is why it is also called as additive manufacturing. This figure is the schematic representation of fused deposition modeling technique, which is one of the category which comes under rapid prototyping. Used 3D printing process is a material extrusion technique called fused deposition modeling. Here, the material is deposited, each layers are fused together. Fused deposition modeling is an additive manufacturing technology commonly used for modeling, prototyping, and production applications. FDM works on an additive principle by laying down material in layers. Metal wire is unwound from a coil and supplies material to an extrusion nozzle, which can turn the flow on and off. The nozzle is heated to melt the material and can be moved in both horizontal and vertical directions by a numerically controlled mechanism, directly controlled by computer-aided manufacturing software package. The model or part is produced by extruding small bits of thermoplastic material to form layers as the material hardens immediately after extrusion from the nozzle. Stepper motors are typically employed to move the extrusion head. FDM, a form is used for prototyping and rapid manufacturing. Prototyping also facilitates iterative testing, and for every short runs, rapid manufacturing can be relatively inexpensive alternative. This is the 3D printer that we are going to use in our laboratory. 3D printer specifications are like this. Printer name is from 1 to 200. Print area is 200 into 200 mm. Maximum nozzle temperature is 260 degrees Celsius. Connectivity, we can use either USB or memory card through card reader, or it can be directly connected to Wi-Fi. Maximum bed temperature is around 100 degrees Celsius. A solid material which can be used in a 3D printing machine can be either PLA, polylactic acid, or acrylonitrile butadiene stearine. So this is the Cura slicing software. We are going to use Cura 15.5, 15.4.3 version for our study. So this is the slicing software in which we are going to slice STL format, standard triangulation language format, into G-code file format. G-code file format is required for a 3D printer to print the component. Once 3D models are generated with modeling software, it is then converted to STL file format. So this is the first window once we open the Cura software. Here we have basic settings and end G codes. We are going to operate with the basic settings. Here we are going to have some, going to change any other default settings. First and foremost thing, under machine menu we have machine settings. Here we have to make sure whether maximum width, maximum depth, maximum height or 160 mm each, and we have to ensure machine center is not disabled. If we enable machine center, it will result in noise and vibration because the coordinates of the nozzle are going to change. In order to avoid the noise vibration, we are going to disable this particular parameter, that is machine setting. Once we're done with machine settings, we are coming out of the window. Now we need to load our HTML file format for the components. For loading, there is an option called load. So these are the three different parts which we require for Geneva mechanism. You can select all the parts at a time and say open. Here we can see the parts are placed on the platform. So this is the platform. If we zoom out, so this is the entire printing area. This is the bed or the platform inside the printer. Now, each and every component can be oriented, scaled, and rotated. So, if we select the component, there is an option called rotate. This is how we rotate the component to 90 degrees. Similarly, all other components are rotated to 90 degrees. You can similarly move the components to any direction, to the any place within the printing area. So once we rotate the component, we can move the components to any other place. Next step, we need to scale the component. For that, there is an option called scaling. Select the component, click on the scale. As required, we can give our desired scaling factor, but one has to make sure that while specifying the scaling factor for all the components have to be same, because this is these are the parts which comes under Geneva mechanism. The scaling factor for all the parts have to be same. Similarly, we can scale this component to 5. Similarly, this component. So this is the support structure we require in Geneva mechanism. Geneva mechanism is one which translates continuous rotation to an intermittent rotary motion. So this is the Geneva wheel, and it is the rotating arc with pin. Now all the three components are scaled to the same scaling factor. We can drag. Now the component is gray in color. That means this particular component cannot be printed since it is outside the boundary or outside the printing area. You have to make sure that all components are yellow in color. That indicates all the components can be printed within the printing area. So these are the basic settings we are going to maintain. Under quality, we have layer height 0.3, shell thickness 1.2. We are going to enable retraction. Under fill, bottom top thickness is 1.2. Fill density is 40%. Print speed is 60. Printing temperature is 200. Second nozzle we don't have, so it is 0. Bed temperature is 60. Support type is everywhere. Platform modation type is none. Support dual extrusion is the first extruder. Since we are having only a single extrusion head, nothing to do with dual extrusion. Filament 1.75 mm is the diameter of the filament which we are going to use in the form of a spool. Diameter 2 is 0. Fill density is 100%. Machine nozzle size is zero point 0.4. Now we can see the duration, total duration required to print all these three components at a time. It is showing 42 minutes. Now there is option called view mode. If I click layers, we can see how many layers are required to build all these three components. It is showing 42. So this is the first layer that is built, and the layers will be increasing gradually to reach number of layers to build the components. If I change the layer height, if I decrease the layer height, number of layers required now is increased. So this is because the layers will be in the form of crisscross pattern. When the layer height decreases, crisscross sectional area decreases. Simultaneously, there is an increase in the component strength. So in our lab, usually we are maintaining 0.3 mm as layer height. So totally it requires 42 minutes to build the components. Let me come back to the normal mode. So this is how we convert STL file format into proper orientation, proper scaling, and proper rotation. When the components are not properly oriented on the platform, it may cause the nozzle to build the components with more perforations. So in order to avoid in pre-processing stage, it is very important to have rotation, scaling, and orientation. The last step here in this software is save tool path. Now we can save this file as we require. If you look at save and type, this is the very important format, that is G code file format. Now we can see the notification. Finally, this is how we convert STL file format into G code file format. 3D printer requires this G code file format in the form of memory card through card reader, or this G code file can be sent to the 3D printer via counterface software. So this is the Praman 200 3D printer. We are going to use this printer in our laboratory. Minimum basic settings of this printer are like this. Once we switch on the printer, so this is the main menu. In this we have to do minimum settings. We have to click on extrude. It will show the printing temperature. The printing temperature has to be minimum 200 degrees Celsius. We have to click on the preheat. In this preheat, now it is showing the bed temperature. The bed temperature is 50. Let us make it 60. Now when we click on the heat bed, it will ask for the printing temperature. It is showing 180. We have to make 200. So these are the minimum settings what we do in 3D printing. Once we set these two parameters, we have to engage the filament into the nozzle head. The filament diameter is 1.75 mm, which is in the form of a spool. We are going to insert the filament into the nozzle head. Now this is the print option. In the main menu we have to click the print option. Now we have to choose the folder. We have selected Geneva Mechanism. In this we have to select the respective G code file format. Select the file, say confirm. It will take some minimum time and the coordinates will be adjusted accordingly. First, the nozzle is going to print the base structure layer by layer. Base layer of the component is printed. So this is the first layer. So like this we will be having layer by layer deposited on the platform. This is how it works. In the software we can see the number of layers required for a component. The first layer is printing. Once the first layer is solidified, then the second layer will be deposited on the first layer and these two layers will be fused. So the process is called fused deposition modeling. Here the raw material whatever we give, that is a solid object, so the process is called solid based rapid prototyping technique. Once the 3D printing process is completed, the three-dimensional objects are printed like this. Now we need to remove the supports. We need to take the plate back, and this is subjected to post processing. Before post processing, these components have to be removed from the base plate. For that, we use some of the instruments. Just we apply a simple force to remove each component like this. From all the sides, a minimum force is required to remove each component. Once the components are 3D printed, these components can be subjected to post processing with suitable device to remove extra perforations like this. Geneva mechanism translates continuous rotation to intermittent rotary motion. So this is the rotating disc, this is the pin, and this is the Geneva wheel. This pin engages the Geneva wheel and it results in intermittent motion of the Geneva wheel as the rotary disc continuously rotates.
3D printing of